All right, everyone, welcome to day 5. So for homework for day 5, you got a couple more problems on packet page 1. Those ones you can do right in the packet. And then on packet page 3, it'll say on there, just like the day 4 homework did, that you need to do those problems on a separate sheet of paper. We're going to go through all the problems one by one. So if you could have that homework out. So we'll start out with the packet ones. So we've got a square root in the denominator. If you try to let u equal what's under the square root, with chain rule, we get negative 2e to the 2x dx. So that's pretty close to what we have in the numerator. We just got to correct by a factor of negative a half. So the negative 1/2 goes out front. Now, rewriting this with our u's, this is something that on Quest 4 I sometimes see errors with. Just because your u was something in the denominator does not mean it's always 1 over u. Notice our u was under a square root in the denominator, so it's 1 over u to the 1/2, or in other words, u to the negative 1/2. Exponent goes up 1, multiply out front by 2, replace u with what it was equal to. Now on the part B, if you let u equal under the square root, we would get that same negative 2e to the 2x dx, but that doesn't match our numerator because we only have e to the x. So this we would want to think under the square root as 1 minus stuff squared. The stuff that's being squared is just an e to the x. So in other words, here we've got e to the x all being squared. So let your u be e to the x, whose derivative is just e to the x dx. Now we've got a perfect match in the numerator. So when we replace with our u's, this sets up nicely for arcsine with an a value of 1. So we have arcsine e to the x plus c. So this continues our pair of ones in the packet where they're very similar looking, and we have to notice the slight differences, whether it's an arc trig or if it's some other u substitution. If we move over to the other packet problems that you did on a separate sheet of paper, so we have our graph drawn there. We're in the first quadrant, the region surrounded by x cubed and cubed root of x. Our area between these curves, I chose to do mine as a dx, so it was a top minus a bottom, so I had cubed root minus x cubed. Now there is consistency right to left as well, so you could have done this as a dy, and you would have ended up getting that same answer as of a half. For part B, we were going over the x-axis, so our region has some gap to it, so therefore this would be the washer method. The blue there is our outer radius. So if we do a top minus a bottom, we get cubed root of x minus 0. So in other words, that outer radius is just cubed root of x. And our inner radius would be that purple. So it'd be x cubed minus 0. So in other words, just x cubed. Our general setup for washers again is pi some radius squared minus some radius squared. That's what will create that hole. And our region dx is we're going from 0 to 1. Do your antiderivative, sub everything, and we get 16 pi over 35. Now when we go over the y-axis, so I'll draw in our example disk for that, or sorry, example washer, because we had a gap. So there's an example of a washer from our region. Here is our outer radius. So when we slice going this way, we are slicing the y-axis, so this becomes a dy. So we would do right minus left. So the right edge is our y equals x cubed, but we would need to know what x equals. So that's x equals cubed root of y. The other one will be x equals y cubed. So our right edge will have cubed root of y minus the left edge of 0. So that gives us our outer radius. Then our inner radius, the right edge is the y cubed minus 0. So that gives us our inner radius in our setup. Y value bounds were still 0 to 1. Do your antiderivative, sub in, we get the exact same thing. Now the reason they were exactly the same is our region is symmetric about that line y equals x. Going over to number 2, we had our region ended up intersecting at x values of 0 and negative 3. We're revolving around the x-axis. So we have gap between our region and the x-axis. So an example washer is going to look something like this. So here is our outer radius. top minus bottom, we've got the quadratic minus 0. So that gives us this first radius. Our inner radius right here would be line minus 0 if we do top minus bottom. That gives us the x plus 6. Then from there, we had to do a little bit of calculating to multiply those out, combine like terms. Our bounds went from -3 to 0, and when we subbed in, you eventually got 243 pi over 5, or 48.6 pi. For number 3, we started out from 0 to 2 with the region between our parabola and the x-axis. So this was our region to start out that was going to get spun around the x-axis. But then a hole was drilled through the middle with a radius of 1. So once that hole is drilled through, basically the part below y equals 1 is gone, and really it's like that purple region only got rotated around. So we do have gap, so therefore it'll be a washer, and our washer will look something like that. The outer radius, top minus bottom, is parabola minus 0. So that gives us the x squared plus 1.1 in our first radius. The inner radius is 1 minus 0, which gives us the 1 there. Multiply everything out, do your antiderivative, sub in, and we get 1903 pi over 150. For 4, we're spinning around the x-axis. So there's gap between our region and the x-axis. So an example washer would look something like this. Outer radius is the upward facing part minus 0. So that's our 3 minus sine x. And then our inner radius is the concave down part. So that's regular sine x minus 0. Multiply that out. We got the sine squareds to wipe out. So then that creates something that we can do the antiderivative of when you sub in. I should mention we're going to 0 to pi for our bounds, but when you sub in, you get 9 pi squared minus 12 pi. And our last one, this was our general ellipse formula. So you have x squared over some a value squared plus y squared over b squared equals 1. So I solved to get y by itself. We got plus and minus under our square root. Now, I kept that b squared out initially, but eventually you're going to want to have it distributed, and you see that in the later steps. So here, we basically want the top half. So we have the positive square root, and our bounds are going from -a to a. We were chopping perpendicular to the x-axis, so we were dx. Now, when we go to take our antiderivative, this b squared is a constant. So therefore, its antiderivative is just the constant times x. And the other term, exponent goes up to 3, divide out front by 3. Sub in your a's and your negative a's and combine like terms, and we eventually get 4/3 pi b squared times a. So what I want to compare this to is our volume of a sphere formula. Our volume of a sphere formula is 4/3 pi r cubed. Basically, in the sphere, you go out r in all directions. Well, in this ellipsoid here, we're going up and down b for our radius. We are going left and right a, and then I can't really draw this on the smartboard, but imagine coming off of the smartboard and going into the wall. That would also be the b amount. So 2 of the directions of our 3 dimensions were b's, and 1 was an a, so that's why that r cubed becomes a b squared times an a. All right, we'll go over to our notes packets for day 5. We're going to work some more with washers today. So we've got y equals 0. Y equals 0 is just the x-axis. We've got x equals 4. And then we've also got square root of x. So square root of x goes through 0, 0, 1, 1, and 4, 2. So that gives us our region, that surrounded part there. And we're going to spin this around x equals 6. So I'm going to put that axis of revolution in as a dotted line. So as we spin this around, we first want to recognize between our region and the line we're spinning it around, there's gap. So because there is gap, that's going to create a washer setup. So we're going to have pi integral. We'll have some radius squared minus some radius squared for our outer and our inner. And then we'll have d something. Washers and disks, we always slice perpendicular to what we're rotating around. So if we slice perpendicular to x equals 6, the axis that would get chopped over and over again is the y-axis. So we'll have dy. In our region, the y values go from 0 to 2. And let's draw in an example of a washer. So here's our outer circle. So it's centered roughly at that x equals 6 and goes to the outer edge of the region. And then here's our inner circle, which is centered at x equals 6 and then goes to the inner edge of the region. So this would be our outer radius. Now keep in mind, before we think about what that is we're dy. So we would want all our functions in terms of y. So keep in mind this equation is really x equals y squared. So for that red outer radius, because we're dy's, we want to do right minus left. The right edge is 6. The left edge is y squared. So we'll have 6 minus y squared for that outer radius. Our inner radius would be this yellow amount here. So we're going to again do right minus left. So right is the 6 minus the left, which is 4. So therefore, we just get 2 for the inner radius. The setup is the biggest challenge. From there, we've got to multiply it out, do our antiderivatives, and sub in. So we're going to pause the video for 5 minutes to let you do those calculations all the way out, and then we'll come back and check your answer and try the next one. So when we multiply out and combine our like terms, we should have got 32 minus 12y squared plus y to the 4th. Do your antiderivative, sub in your 2. We get 64 minus 32 plus 32 fifths. The 0 gives us 0 for everything. And combining your like terms, getting a common denominator, we get 192 pi over 5. If we move down to our second example, we're going to start with the same region. So let's take our y equals 0. We'll take our x equals 4. And then we'll take our square root of x that went through 0, 0, 1, 1, and 4, 2. And we'll work with that region again. The difference is now we're going to go around x equals negative 2. So I'm going to draw that axis of revolution in with a dotted line. Because there is gap between our enclosed region and the line we are rotating around, we're going to have a washer's case. So we'll again have pi integral. We'll have an outer radius squared minus an inner radius squared, and then d something. Slicing perpendicular to what we're rotating around, that would cause us to slice the y-axis. So we've got dy again, 0 to 2 for our y bounds, just like the last time. I'm going to draw in an example washer. So our outer circle should keep that x equals negative 2 as the center, and then go to the outer edge of our region. The inner circle should keep that x equals negative 2 as the center, and then go to the inner edge of our region. There's our outer radius. It's y, so we're going to think right minus left. So the right edge is 4 minus the left edge, which is negative 2. So 4 minus negative 2 is just going to give us 6 for the outer radius. For the inner radius, we will do right minus left again. Keep in mind we're dy, so we want to think of this equation as y squared equals x. So our right edge is y squared minus the left edge, which is negative 2. So we'll end up with y squared plus 4 from there. We're going to pause the video for 4 minutes this time, and we'll see if you can go through and do our antiderivative and find the volume. Before you go, just note I miswrote there. That's minus a minus 2, so that's a plus 2 here, not a plus 4. So now we will give you 4 minutes to try this volume. All right, after you multiply out combined like terms, you should have had negative y to the fourth minus 4y squared plus 32. Do your antiderivative sub in the long run, you get 704 pi over 15. Your common denominator terms were negative 96 fifteenths, negative 160 fifteenths, and 960 fifteenths. All right, if we go to the next page, we're going to again start with the same region. So we'll be working with a region that's bound by y equals 0, x equals 4, and then our square root of x, which goes through 0, 0, 1, 1, and 4, 2. The difference now is we're going to revolve around y equals 2. Notice that there is gap between our region and y equals 2. So we will be working with a washers here. We'll have pi integral. We'll have some radius squared minus some radius squared. And you'll figure out the d in a second. We're going to actually reverse things, and we're going to let you try for 3 minutes to figure out the setup, and then we'll come back together and do the integral together. Okay, so go ahead, see if you can figure out what the setup of this volume would be. Slicing perpendicular to what we were rotating around, we should be slicing the x-axis, so we get dx. Our x's in our region go from 0 to 4. If you draw in an example washer, there's our outer circle, maybe with it going a little too high. There's our inner circle. So here's our outer radius. So if we do a top minus a bottom, that gives us 2 minus 0. So the outer radius is just 2. If we do our inner radius, which would be right here, we've got square root of x. Sorry, not square root of x. I drew the radius in the wrong spot. Let me fix that. Our inner radius is right here because it's got to attach to what we are spinning around. So if we do a top minus a bottom, it's a 2 minus the square root of x. And square root of x is okay in this case because we decided we are dx. So we'll put the 2 minus square root of x in here. We'll multiply these out. We'll have 4 minus, start a parenthesis. We'll have 4 minus 2 square root of x. Minus a minus will give us a plus, so then we'll end up with a plus x. If we distribute our negative and combine like terms, the 4s will end up giving us 0, so we'll just have a positive 2 radical x minus x dx. Our antiderivative, we have x to the 1/2 currently, so we'll now have x to the 3 halves. So we'll divide out front by 3/2, which is the same. Wait, I made an error here. Sorry. I got to fix something. This should be a 4. So therefore, this should be a 4. So our new exponent is 3/2. Divide out front by 3/2, which is the same as multiplying by 2/3. So that'll give us 8/3. X's new exponent is 2. Divide out front by 2, so we'll get -1/2. And we're going from 0 to 4. When we sub in the 4 to that first x, square root of 4 is 2. 2 to the third is 8. 8 times 8/3 is 64/3. 4 squared is 16 times the -1/2 gives us -8. And all the other parts are 0. 8 is really 24/3, so 64/3 minus 24/3 will give us 40 pi over 3 for that volume. Moving on to the next one, we're going to work with a new equation now. So we've got those 3 green ones there, what are going to surround our region. So we've got x equals 3, which is a vertical line. We've got -x plus 1. So that has a y-intercept of 1. And it'll go down 1 and over 1 each time. So therefore, it's going to intersect our line at 3, -2. And then we've got e to the x. Well, e to the 0 is 1. And then it's going to look like exponential growth. So this point right here is going to be 3 comma e to the third. And we are going to revolve this around that x equals 3. So 2 things that are different with this example compared to the other ones. There's no gap between our region and what we're rotating around. So this is going to be a disk as opposed to a washer. One other issue we have to contend with is we're going to be slicing this perpendicular to that x equals 3. So we'll be doing horizontal slices, which will chop the y-axis. So this is a dy. When we work with y's, we do right minus left. But when we're working with right minus left here, notice the leftmost edge of our region changes. The upper part of it is bound by the e to the x, and the lower part of the left edge is the -x plus 1. So because of that, we're basically going to have to do 2 separate volumes. We'll do the volume above that yellow line that's at y equals 1, and we'll do the volume below that, and they'll each be disks. So let's work with the one above to start out. So here's an example disk. We'll have pi integral. We said we're doing disks, so we'll have something squared, and we said we're doing dy because we're slicing horizontal, so that would chop the y-axis. Our bounds for our y's in that region above the yellow dotted line there, we're starting at y equals 1, and we're going to y equals e cubed. There's our radius. We want to do a right minus a left. So our right edge is 3 minus the left edge is e to the x. But that's a problem. We can't put that in our integral because we're supposed to be dy. So rather than having e to the x, we've got to decide, well, what's x equal to in that equation? If we switch to log form, x is equal to natural log of y. So we'll really have 3 minus natural log of y. So then we're going to add on our volume for the bottom section. It'll again be a disk, so we'll have pi integral something squared dy. Here's an example washer for that region. Our y value bounds for below that yellow line, we're going as low as -2 and as high as 1. Here's an example of our radius. We'll do a right minus left, so we're doing 3 minus the line. But we've got to do the line in terms of y. Here we have y equals -x plus 1. If we add the x over to the left and subtract the y over, we get x is equal to 1 minus y. So when we do 3 minus that, we've got to make sure to put the 1 minus y in parentheses so that negative distributes to both of them. If we distribute that negative, minus the minus will end up giving us a plus y, so we'll end up with 2 plus y in the long run. And that'll go in for our other radius. So this one, I was going to have you do on the calculator. I'm assuming you could punch this in fine in a calculator page. In the long run, it will end up giving us 101.068. And we're going to stop with that problem for this video. You've got the day 5 homework. Remember the 2 problems you could do right in the packet where we've been doing all the other packet ones, but then the packet page 3, make sure to do those ones on a separate sheet of paper. Have a great rest of your day.